I'm very honored to be there and to introduce this talk. I think that all the speakers here are not only brilliant people, as you can hear, but they all have a vision of what is robotic research and what it should be and what is their particular field. And Russ Taylor is one of these very inspiring guy along my research track. I got to know him for his initial work in more classical, let's say, robotics and his development of the AML language in IBM, where he joined the IBM research after his PhD in Stanford that he received in 1976. And there he had the responsibility of the automation technology department, and later he started the computer-assisted surgery activity at a time where medical robotics was only the fact of very few people worldwide. And there I developed the Robodoc system, which was very famous and which I really think made the medical robotics sometimes controversial, but also very attractive, and it's a very dynamic domain. And I think that Russ is one of the guys. Paolo also sure is one of the guys that really promoted this field. Okay, he stayed in IBM until 1995. And then he joined the Johns Hopkins University, where he's a professor and is director of the Excellence Engineering Research Center for Computer-Integrated Surgical System and Technology. And I think that the talk will present a lot of this work. He has published many papers, of course, and he's a fellow of a number of scientific societies and universities also, and he received several awards, and I want to name three of them because they really show what is his achievement and contribution to the field. He has got the IEEE Robotics Pioneer Award, telling about his contribution to the fundamental field of robotics. He got also the Mikai Society Enduring Impact Awards that tells how important is his work in medical robotics. And finally, the Maurice Muller Award for Excellence in Computer-Assisted Orthopedic Surgery, and that tells how the great impact that you had in computer orthopedic surgery, and we're very proud to hear you, Russ. Please.
Thank you. Before I start, first let me just thank my hosts for inviting me. Also, I really am honored, Jocelyn, by your introduction. You were one of the few in that field, as well as me at that time, and one of the very, very early clinical systems you were essential in helping develop. So. Thank you very much. What I am going to be and also before I start my talk, this isn't just my work. As in most of robotics, but especially in medical robotics, you realize that it is really important to work in teams. Problems don't neatly fall into our disciplinary training, and I really have to thank all of my collaborators and some of the organizations I've been lucky enough to work with. I'll try to acknowledge them as I go along, but I just wanted to start with that. The motivating, Mike, your talk, in a way, we and Jocelyn all made this transition from early looking at manufacturing problems and beginning to look at medical problems later. And these are two of the systems that I was involved with at IBM. Now, one of the really interesting things is these systems, they look kind of different, but fundamentally they couple information to action, and often in partnership with people to fundamentally change processes. And that will be, I think, the main theme of my talk today. Jocelyn mentioned Robodoc, which was my introduction to this area of medical robotics. And here what we were doing is we were planning an orthopedic procedure, a hip replacement surgery, from the images, and then we used a robot to help the surgeon very, very accurately carry out the plan. And it produced a much more accurate execution, and although you don't see it here, and I think more importantly, a less traumatic execution. You didn't break the bone. So at IBM, I put together a slide that looked like this to explain to my bosses why an information company should be interested in something as exotic as a medical robot. And if you look at it, the basic idea is you start with everything you know about the patient. A lot of that is in the form of medical images. You need to represent that in the computer, and I'm going to call that a model. Basically, I mean any data structure that lets us do the rest of the process. Well, you can diagnose a patient's condition, as Mike says, then you can plan your intervention. Well, very, very crucially, you can take all of this information into the operating room or intervention room with you. And if you can then register, if you can fuse the virtual reality with the reality in the operating room, then you can use a variety of technology to help the surgeon do what was planned and to verify that it's been done. Well, basically, I'm an engineer, and to me that's a control loop closed with information. You notice this picture up here has that same shape? What that is really to remind us is this basic information loop really occurs at many, many different time scales, from treating an entire patient cycle right down to second by second in the operating room. The other thing, if you have computers and machines involved in this process, you necessarily are generating lots and lots of data. You can be consistent and you know what you did. Eventually, we know the outcome. So if we can just save that information over time, we can begin to use statistical methods to help us improve our treatment processes. And I believe that it is the synergy between these blue loops and this red loop ultimately that is going to drive a change in medical practice. That was also the theme of, certainly was the largest proposal I've ever written, of this engineering research center where we had a fair amount of seed money from the United States, from the National Science Foundation, and a number of small universities that we were able to work with to pursue this theme. One thing with these NSF centers, that they really expect you to make contributions to fundamental knowledge and technology, but driven by complete engineered systems. And these are basically the pictures from our first site visit. And this is the last time I bothered to make that. And don't worry, we don't have time to talk about all of that, or even the things that didn't make it. So what I would like to do is I would like to use this picture to use examples from our own work to illustrate each of these blocks as we go. First, if we look at modeling, well, Mike has set this up just beautifully. What we're trying to do is extract information, a lot of it from images, and put it into a form that we can use to diagnose, but then to plan interventions. Generally, we're dealing with surgery, and generally we're focusing on anatomy, but more and more looking at the biology, tying it to the anatomy is becoming important. Also, increasingly you need to refer to statistical, we call them statistical atlases, statistical models of anatomical variation. I might just mention this is some recent work on real-time deformable registration that one of my graduate students has been doing. Just to illustrate one theme, you could talk for entire symposia on medical modeling, is taking what you already know, both about the specific patient and about people in general, and combining them with new information, new images, to create a better or an updated representation of the individual patient. And how this is done really depends a lot on the imaging and the applications, but here are just a few examples. This is we actually recorded the video, and then this is done offline for illustration purposes, but this is a patient with a kidney tumor that we've observed with stereo TV from a Da Vinci robot, and then what we've done is we've fused the stereo video with the models. Now that red line, which you would see in stereo, is the 5mm resection margin. That's the cut here line. And the idea is to provide the surgeon with some additional guidance. Here he can see the tumor, but very often the tumor is hidden down inside the kidney and it's harder to see. Okay. Here's another example. This has actually gotten into clinical use where we have a cone beam CT scanner. What we've done is registered preoperative models to intraoperative visualizations of the tumor. This here is a cadaver study, and then you can see cone beam. Now, this is primarily the work of my colleagues Jeff Sewardson and Greg Hager and their students, but one of the goals is, as you're doing surgery, the surgeon would like to see how the patient has been changed so far. Here's another example. This is from one of my students' work, where we're trying to plan an osteotomy for patients with hip dysplasia, which is quite common in young women. And what they do is they cut the pelvis into segments and move it around to prevent dislocations and bad wear on the cartilage. You don't want to put much radiation, if you can help it, into the pelvic area of a young woman. So the idea is to take CT scan only of the cartilage area and combine it with statistical information and a small number of X-ray images to get a good enough model of the pelvis so that we can actually plan and then register and carry out the intervention. I mentioned planning. Again, this is a very, very wide area, and the details are very specific to what the procedure is. A couple general points. This was a RoboDoc planning screen. Generally, it occurs at many, many different time scales, and one of the problems that is still open is how do you fuse and do dynamic replanning in the operating room effectively based on images and models, and there's a lot of computer science buzzwords of various sorts involved in it. Typically, again, what you're trying to do really depends on the procedure. Oftentimes we're dealing with geometric information like toolpaths or targets. Sometimes just visualizations where the surgeon says, I want to get to a place where it will look like this. Again, if I look at some of these themes, one of the main themes is more and more interest in fusing statistical information about prior procedures, prior cases to help us plan this case. I don't have a lot. I'll come back to that at the end of my talk. Most of the time I'm going to be talking about execution because this is really where the robotics come in. But I want to start with this picture, which is really to remind us you don't need a robot always. And in fact, Often, if you can do without it, simpler is better. Here, the idea is very simply, if you take a mirror and a display of a cross-sectional image of the patient, you can line things up so the virtual image coincides with the physical position of that slice in the patient. Then you can use hand-eye coordination to, for instance, place a needle accurately. And finally, we're close to getting into clinical use for in MRI injections in the periacetabular region. Here is a fairly recent cadaver study of that work, which has mainly been led by my colleague Gabor Fichtinger, but actually started with some work of Ken Masamune in Japan. Here's a robotic case. Again, this is quite an old example where what we're doing is we're going to be biopsying a kidney tumor. But the interesting thing is the needle driver has fiducials on it, so that by looking at the fiducials, you don't have to see the needle to know where the needle is. And crucially, what we're doing now is we're closing the control loop through the image rather than through a very long calibration chain of the robot being attached to the table. And I think that's a very, very important theme in a lot of what we do. Here's another work currently being led by Peter Kazantzidis at Hopkins, where we're, for ultrasound-guided transrectal guidance for prostate seed therapy. And Jocelyn, you've done a lot of work, I think, in this general area as well. Here's another example where, in this case, this is transrectal MRI guidance, where here's the sense coils for the robot, although initially this robot was just simply manually actuated. And again, the key thing is you're closing a control loop through images. So here are the targets. Here are voids from the experiment. And the thing that was amazing to me is this went from literally the back of a placemat to clinical use in under 2 years. And in our field, that is very unusual. This is some more current work being led at Hopkins by Julian Yordakita, where we are working with Brigham and Women's Hospital, and it's an NMRI system for prostate brachytherapy. MRI, you can see cancer and tumors a lot better than you can in ultrasound, and there's a lot of interest, therefore, in using MRI, both to guide biopsies and therapy. I can never predict how long these talks are going to go. Mostly, all of those robots have been really about aiming the needle, not placing the needle. Very thin needles, and you want it to be thin, generally, tend to deflect. They all have a little bevel at the end of the sharp part of the needle, and it deflects the needle. Well, what a robot can do, what a good interventional radiologist can do, if you twist the needle as you insert it, you can steer the needle like a bicycle. And so we've had a project started and led mostly by Allison Akamura, but also including a fairly large team of people to exploit this idea to improve accuracy of needle placement and also to avoid obstacles. This work is just about finally to get into animal trials. Providing high dexterity or high degree of configurability in very, very small spaces is a mechanical engineering challenge, and there have been a number of approaches. This is one that we were involved with very early at Johns Hopkins, and some people at BU have also been pursuing this idea. If you have nitinol, super elastic material, and you bend it, and then you rotate and translate these tubes relative to each other, you can get large and interesting shapes. There's also some early work in Europe, I'm drawing a blank, from TU Munich on similar ideas. So this is one of the things that is being done. Here's another approach that Nabil Simon and I pursued at Johns Hopkins, where, again, we're really relying on the superelasticity of nitinol. But if you have parallel links and you hold them kind of parallel and you push on one and pull on another, you're going to get bending. So what we have here are 3 tubes, and running through each tube is a wire. So we have actually 4 degrees of freedom and then actuating a little gripper. And the point is, this can be scaled. This can be made quite small. This one is 4 millimeters across. So here we have higher dexterity in a smaller space than the Da Vinci robot. And it's very important to keep mechanical simplicity as you make things smaller and smaller and smaller, because it gets harder to make all those little bearings and pulleys and pivots of robotic mechanisms. Here is my colleague Nabil Simon, and this should start playing, has carried this rather further. Here is his prototype of a single port axis robot. These are, I think, a little larger. I believe these are about 6 millimeters across. Now, one thing with these single port access, with laparoscopic surgery, they put a camera through your belly button and then stick additional tools in through additional entry ports. Here, the idea is to do all of that in one port, so there are fewer entries, but also you can get in to a smaller area, volume inside the body. And there's quite a lot of interest in this now. Here's another robot. This is something that we've been exploring at Johns Hopkins. And it was originally motivated by an application in bone cancer, where what we wanted to do is to clean out a bone cancer lesion without having to cut open and make a major cut into the bone. In this case, initial application will be particle wear disease, or what happens is if you have from the cup, the liner of an orthopedic implant, you get little micro wear particles that can work in behind the implant, and it sets up, you can think of it as an allergic reaction in the bone. And what that does is the bone back there turns to mush. You can see it. They can even replace that liner, but if they don't clean that out, it's going to keep getting worse until you have a failure. But until you have that failure, the patient has no symptoms, so what do? So our idea is to get in either through a port through the bone, or in this case, if you're replacing the liner, come in through holes in the implant and scrub out that lesion from the inside with little brushes and the like. So what we have here is a metal, it's again nitinol, tube with wires embedded in the wall. This is got a 4 millimeter lumen in a 6 millimeter tube, and it's really quite stiff and strong, so we can scrub this lesion out from inside the cavity. And we have some pending proposals right now to take this to the next step. And I think, again, it's illustrative of how a gadget can enable you to do something, but again, we need to put around it all of the guidance and control and planning. Here's another application for that same robot, and this is some work we're doing with Philips. There is a problem, militarily, it's from roadside bombs in Afghanistan, but also in civilian life, you can get from explosions or accidents, you can get little particles of metal or stone or whatever that get into your circulatory system. They get up into the heart where they bounce around. Now, the problem is if one of those makes it up into a lung, you've got a dead patient. The standard treatment is open heart surgery, and it's quite a major procedure. Here the idea is to have a minimally invasive approach in which we come up through the apex of the heart and have that robot, that steerable robot, deploy some means of capturing the particle, like a little suction device or a little net to snare it. Well, there's a problem. Things in the heart move around very fast, and you can try to chase it. There's work at Harvard and also some very good work in Strasbourg to try to make a very fast robot to chase things in the heart. What we had in mind, though, is a rather simpler idea, which is to realize that these particles get trapped into eddies and they bounce around for a second and two and go somewhere else. And so by watching, we can predict where that eddy is and make like a bass and wait there and ambush the particle. And so that's what the approach we're pursuing. We're just about to start some experiments to do this on the actual snarfing on phantoms, and then I'm hoping within a year to be doing this in some pig labs. Telesurgery is certainly, when we say medical robots, this company, Intuitive Surgical, they're certainly the most successful commercially. There are several thousand of these machines deployed around the world, where the surgeon sits here, looks into stereo video, moves some control handles, and the robot follows his hands. And Mike showed you some video. You don't always have to have that complex a robot, and this was just a little project that one of my students did, a very, very larsimple project to basically manipulate steerable endoscopes in laryngeal surgery, or with some modifications for bronchoscopy. And one of the things here, we're just in the final stages of going back to the FDA for approval to use this on patients. But also the strategy here is to get something into use and then begin to make it smarter. And to some extent, I think we've seen that beginning to happen with the more sophisticated robots. And this is a bad, what appears to be about to happen is Microsoft is about to complain that I'm going to have to restart this, I think. I'm sorry. Somehow Bill Gates doesn't like large files, and this one's a gigabyte. Whoa, that's even worse. Hang on. So I was afraid this would happen. Maybe it won't die now. Where are we here? So here you're also seeing many of the things I decided that I didn't have time to tell you about. Oh, okay. Well, I'm seeing many of the things I decided I did not have time to tell you about. Let's try this. Now let us say here. Oh dear. There. Okay. If you look at that interface, one of the key things that we've done is we put a computer between the surgeon and the patient. So we ought to be able to use the power of the computer to enhance that interface in various ways. And this is, of course, a major theme of our research. Here's just one example. This is a project we did with Intuitive, where what we've done is we've equipped the robot with an ultrasound, laparoscopic ultrasound probe to give the surgeon the feeling of doing open ultrasound, but inside the patient. Also you can do things like these virtual augmented reality displays and the like. One of the keys, if you have ultrasound, you'd like to relate it to what you're seeing in the patient. And so this is some very, very recent work. This is the first time we've really talked about it, where we're using what's called the photoacoustic effect to help us do registration to ultrasound. Here we have a 3D ultrasound. If you flash a bright pulse of laser light onto tissue, it is absorbed, expands momentarily, and gives off sound wave. It's lightning and thunder. And so if you flash a pattern that you can see in an endoscope, and you can see it in the ultrasound, you can fuse those. And so this is what it looks like on phantoms in our lab. Here you can see just one of the spots. Our student Alexis Cheng has been getting better than 1 millimeter target registration errors this way. The standard using conventional ways of registering ultrasound to video, you're doing well if you get 3 millimeters. So this is very direct and very accurate, and we're really pretty excited by it. One of the other things you can do, though, if you have the robot, is it can help you combine it with ultrasound to do various other things. One of the things you can do, if you push on an ultrasound sensor and track the speckle, you can compute the relative stiffness of tissue. This is called elastography. You don't need a robot, but if you use a robot, you can do a lot better. So here what we've done is the surgeon guides the probe, and then the robot automatically is programmed to add a palpation motion. I should mention that we've been very lucky to get access to the application programming interface of the Da Vinci and built some of our own software on top of it. I'll talk maybe a little about that later. So here, this is a phantom, and that's the lesion, and that's what it looks like in just regular ultrasound. Here's another project. The first time we've really talked about it, where our surgeon, Jeremy Richmond, does a lot of transoral surgery on tumors on the base of the tongue. They're getting more and more common, most of them coming not so much from smokers, but from human papillomavirus. And the idea is to use imaging, intraoperative imaging, cone beam CT in our case, to locate, to image the tumors and then fuse that back to give the surgeon a view. Here's on a pig tongue phantom. This is just one of the initial experiments we've been doing, and kind of shows you here, the goal isn't so much to place a needle, would be as to guide a resection, but this was just simply to help us verify that we had our information loops reasonably good. And we're getting, as I recall, about 1 or 2 millimeter accuracy in that, as I recall. And I believe here'll be another one. I'm about to talk myself out of time, so I should probably push on, especially because things may crash again. But in any case, this is some of the work that my student Wen Liu has been doing. She'll be talking about this at the Hamlin Symposium in London at the end of the month. This is some work, again, that Nicholas Padoy has been doing, where if you watch surgery, the robot can learn sort of standard surgical maneuvers by watching. We saw some earlier examples of learning. And here what's happening is the robot is automatically trading off control of the robot with the surgeon. So the surgeon is doing this. This is not a very good surgeon. One of the other uses of this sort of analysis is actually to automatically test. You can distinguish between skilled and not so skilled surgeons. And then the robot again takes over and completes the stitch. I don't personally find this all that plausible, except as I don't think a surgeon would really want you to do this. But as a driver, it is useful. Now, here is a scenario that I think is fairly common. The robot can be your surgical assistant. So the surgeon has held up a suture and said, please cut here. And the robot is now knowing to come over and cut. And again, here's another, in this case, he's just going to grab the suture, but the human will, and now the computer comes and finds the thread again, and the robot will know to come over, in this case, grab it. If those were scissors, it would cut it. And I think this is about the state of the art. This stuff here is a long way from being deployed clinically, but it is part of the trend of where I think we may be headed. I'm going to talk a little longer about what is, I think, our largest single project, at least in my group right now, which is a system to address some of the difficulties in vitreoretinal microsurgery, which is arguably technically one of the most difficult surgical disciplines. You're having this tools are less than 1 millimeter across. They're inserted through the eye. The surgeon has very poor ergonomics, not really great visualization. He's staring into this microscope. Most common cause of occupational disability is neck pain. You have hand tremor. The forces between the tool and the tissue are an order of magnitude smaller than humans can feel. So it's an extremely difficult surgery. So our goal is to develop a system that addresses some of those limitations, human-machine limitations in retinal surgery, and integrate them into a complete system, and eventually to get this into clinical use. Here's a system block diagram showing some of the components. There are robots of several sorts involved. The heart of it really is the information workstation tied to a stereo video microscope. And if you look, here's what the system looks like in our lab. I'll be talking about some of the components. Here's what it looks like in the clinical lab. We have an old operating room at the medical campus that we use for in vivo experiments on rabbits, and in this case, one with the robot. And I'll be talking some more about this. I mentioned we have a stereo video microscope, so the computer can see what the surgeon sees and display it. And then you can process that. Here what we're doing is we're tracking the retina. You have a very limited field of view, and so here it's kind of montaging a larger view. And then the surgeon, here, if you annotate with various ways, in this case we're just drawing, if you annotate the retina, it can track that. Another thing we can do is we can register preoperative fundus images to intraoperative images and transfer preoperative information that way. One thing here, of course, the surgeon then has to look away to get the context information. So here's just another way of displaying the same thing. I might just mention rabbit retinas look rather different than human retinas. They have this stripe, and what's out here is basically not too interesting. But this is, again, these are fairly recent images. We have here, one of our partners, our collaborators in some of this work are Carl Zeiss Meditech, who've provided us a loan of a really good experimental video microscope, and we're very grateful for that. Okay, well, knowing where the retina is useful, but you've also got to know where the tool is. And so here is tool tracking. This environment, you'd think it's really simple, nice, open, simple geometry. It's enormously difficult environment because the lighting changes so dramatically. It's very, very difficult environment. There's glare, reflections. The appearance models of the tools are not what you'd like, but we're also developing ways of tracking tools relative to the retina. This is on a phantom, and here what we're doing is we're basically generating a warning when the tool is getting close to the retina. And here are the relative distances, and this is a force sensor that is saying, oh, you're touching the retina. Again, I think an experienced retinal surgeon would not be so enthusiastic about seeing that, but if he's mentoring one of his residents, he would be glad to know. And so the computer can also change its mode depending on how close you are to the retina. Robotic devices, there are several that we're exploring. This is one of our collaborators is Cam Revere at Carnegie Mellon. And in this case, he has a robot that is handheld, and you can sense the tremulous motion of the surgeon, and sort of like these noise-canceling headphones, you have a very fast little robot that kicks the other direction to cancel the tremor. Or you can also close control loops between using external sensors. So here is, up here was what that looked like, freehand, and it'll come in, and down here is what it looks like with the robot. And it's a little difficult to see, but in fact, it's a lot more stable. We've just started to use these systems on rabbits. The one we're using is a little newer, and the surgeons actually like this. Here's another technique. These are what we call our steady hand robots. The idea here is really very simple. The surgeon and the robot both hold the tool. You have a force sensor, so if you pull on the tool, the robot will feel that and follow your hand. Of course, it's a robot. It can not follow your hand. It can enforce a safety barrier, or it can share control with the surgeon in various ways. But again, because it's a robot, this has no hand tremor. And just to show you that, one of the applications is to insert a pipette into a blood vessel that is the diameter of the hair on your head. The idea is if you have a blood clot in your eye, if you could get a needle in there, you could inject something to dissolve the clot, but you have to hold the needle there for about 5 minutes. And it's really not practical without something like a robot to help you. So this is freehand. That is a live video. If you were watching very carefully, you would occasionally see a bubble come up there. The other thing, an awful lot of retinal surgery is peeling membranes off of the eye, something called either an epiretinal membrane, which is about 25 microns thick. It's basically scar tissue. It's like tearing sticky tape off of tissue paper without tearing the tissue paper. Or there's another thing called the internal limiting membrane, which is about 3 microns thick. Here again, this is just a more recent robotic example of that cannulation here. Yeah, you can see how delicate the tip is. Here we're cannulating a chicken egg, and this was a little older than most of the chicken embryos, and that vessel was really very tough. But this is the kind of thing we do. Force, this is, as I said, the forces are an order of magnitude smaller than you can feel. And the force between the tool and the sclera is larger than the force between the tool and the tissue. So this means you have to do the sensing inside the eye. And so what we've done is we've built optical fiber strain gauges, fiber Bragg grading sensors down into the shaft of the tool, and we're getting about 25 millinewton, 0.25 millinewton sensitivity. Here's another tool. This one is a forceps tool just to show some of the kind of things we do. Now, how do you, these are out of order or something. Let me just, no, okay, we'll keep going. Here, how do you tell the surgeon the forces? You can feed them back haptically if you have a robot, but if it's a freehand tool, you can't. One thing is to use video. So here we're basically showing the surgeon forces. Oddly, the surgeons don't like this. They're saying, why distract us with all this visual stuff when I really want to concentrate right here? So what we have been doing more is we've been feeding forces back through auditory channel. And so as you get up to various threshold limits, we change the tone. And so this is the sort of thing we can do. You can tell the surgeon how hard things are pulling. And grad students can have fun in the evening. Experiments, here again are some in vivo experiments we've been doing with this. One of the things is no one really knew what the forces on the retina were in surgery. So we're now able to do various surgical maneuvers and tell, and beginning to get a sense of the force profile that corresponds to damaging the retina versus not damaging the retina. And one of the key things from taking a systems approach is every signal in our system, all the video, all of the force, all of the other sensor data is recorded together. And so this was, and then you can go back post-operatively and you can analyze that data. And here what we're doing is we're actually identifying the force profiles that correspond to tearing the retina. It's not just absolute force. There's a very characteristic change in the rate of force as something's getting ready to tear. Of course, if you have a robot, you can do some more things. You can actually feed back to the robot and control forces, or you can do some other things as well. This was a very, very simple control strategy that was intended to provide haptic feedback for blunt tissue dissection. Basically, the robot wants to go in the direction of least resistance. And it turns out that if you're wanting to tear, it just naturally gets you to peeling something at a 45-degree angle. Or this was tearing a membrane on the inside of an eggshell. And the surgeons got very excited when they saw this, because in cataract surgery, there's one of the standard and difficult to learn steps is something called capsulorhexis, which is basically tearing a circular hole in the lens of the eye so they can extract the lens. It's in the covering over the lens of the eye. And it turned out the robot just naturally helped you do that motion. Another sensor that we've built in is optical coherence tomography sensor. OCT, you can think of it as ultrasound with light. It's an interferometric technique, and you can get here by taking a sensor scanning, you can get delicate structure. The particular technique we're using is so-called Fourier domain OCT, which kind of, as a side effect, you get the tissue spectrum. And so here what we're able to do is tell oxygenated hemoglobin from not oxygenated hemoglobin and get some functional information as well. Well, one of the things you can do is you can build the feedback, in this case just simply the distance to the retina, directly into the robot and close control loops in the robot this way. And you can do this either with a fairly slow robot like that steady hand iRobot, but also with that very fast Micron, the CMU device. So these are some of the sorts of things that you can do by combining sensing with the robotics. Here's a behavior that we can do either with or without the robot. I mentioned membrane peeling. What you want to do when you're going to peel sticky tape is you want to find the edge of the tape and to begin to work it up. That's very difficult often to see through the microscope, but you can see it in OCT. And so here what we do is we take the OCT tool, scan it across the retina. And here we say, here's where we've scanned. Here's the OCT, and the defect we're looking for, the edge is about there. But then if you point at that line, which tracks with the retina, that's like one of the annotations. It says, okay, right there, here's the close-up. And it can actually help you find the target to begin peeling. So this, again, we're doing on phantoms right now. We're just starting to do this on rabbits. Again, this is one of the more researchy directions. Feedback is really very, very important. Doing is important, but you also need to monitor what you do and evaluate what you've done. Here's an example, again, coming back to that elastography idea. This has been done clinically, where here what they're doing is monitoring ablation. If you have, in this case, a liver tumor, you can insert an RF probe into the tumor and basically cook the tumor from the inside out. The standard way of doing that is they stick it in, I'll cook for 10 minutes or however long. But of course, liver isn't all that homogeneous. You have blood vessels that take heat away. What you'd really like to do is cook until done. Well, if you do this elastography, you can actually see the meatball cooking. You can see the stiffer tissue that has been ablated, and it's a little like testing meat on a grill. And so this is what we're seeing. Here is the ultrasound, here's the elasticity image, and here was the corresponding postoperative CT. Here's another example. This is an orthopedic example. If you have a patient with osteoporosis, you know that patient is at high risk of fracture. They may have already broken their other leg. You can wait until they break their leg and try to fix it, but maybe the idea is if we could get in and intervene, for instance, stick a needle into the bone and inject some cement, we could strengthen the bone to prevent the fracture. Well, you need to know what that cement ball looks like. You could do intraoperative cone beam CT, but there are various reasons it can be difficult because there are things in the way and it's a lot of radiation. So here, just with a small number, I believe these are done with 4 images and some other work from my student Blake Lucas, we're able to get a very good representation of the cement ball, much better than you would get just by intersecting the outlines of the cement. Well, that's these loops. Let me just say a word or two about the red loop, the process loop. Again, to me, from the very beginning, one of the first things that we talked about in doing Robodoc is exactly we can now begin to compare different implant designs. That was the original motivation of the surgeons who wanted a robot to help them do the intervention. But also in manufacturing, IBM, we kept all sorts of records. So if you had, say, a yield problem on a disk head line, research, we'd go out and we'd maybe do some more instrumenting. But often, since they'd saved everything, you could do data mining and you could often know where to look. And so it's always been my dream that we should be able to do that in interventional medicine. And I think this is just saying that. The themes here, we're talking, in the US, the phrase big data has become popular. But this, I think, is an example of that. If we could just mine the entire patient database, and if we add to it and we know what we really did, we can begin to do various statistical modeling, maybe online track procedures, to help provide, even in real time, tell the surgeon, here is what this looks like. If you do this, here's the likelihood of outcome A. If you do that, here's the likelihood of outcome B. So this is a major theme. Here's one example I've been involved with in radiation therapy planning. Radiation therapy planning is both computing intensive and labor intensive. And the idea is, it's also, there's a lot of data, and the idea is, could we take a database of all our experience from previously treated patients to help us improve both the quality and the efficiency of planning the next patient. So the way this works, and normally what happens is you get the information about all the structures. Here's a tumor. These are the salivary glands, the brainstem, and the spinal cord. You want to kill this, but not hurt more of those than is recommended. Somebody like a dosimetrist sets up an optimization problem that computes machine settings that try to do that. And then they simulate the dose that those machine settings would get. Typically, the dosimetrist says, oh, no, because it's not very good. He then changes the settings a little and goes around that loop maybe 15 times until there's something that the dosimetrist thinks the clinician will accept. And he thinks is as good as he can do. Needless to say, there's a lot of variability as a result of that process. Our idea is by looking at the relative geometry of the surrounding structures and the tumor, and basically we compute something we call the overlap volume histogram, which is basically what fraction of each of these are within what distance of the tumor. We can index our database, and we can find patients who are most similar to the current patient and start with their optimization plan. Or we can look and we can say, are there patients who should be at least as hard to plan, but whose plans spared these surrounding organs better than the one we're about to treat with? If you do that, and then what you can find as quality control measure, and I can't remember the number, I think it's about 15% of cases we were able to identify you can significantly improve the organ sparing. Or if you just take our machine-assisted plan and a normal manual plan, put them side by side, the dosimeter or the clinician will say either they're indistinguishable or the machine one is better. So this is just now getting into the clinical workflow at Hopkins, and something we're really very proud of. Here's one final example. Here the goal is you'd like to assess, get some feel for, over time, how critical is the placement of a tunnel that they drill in through your bones for ACL tendon replacement to the outcome. It's believed that that tunnel is very critical, but no one knows exactly how much tolerance is acceptable. So the idea is eventually you know some number of these fail. Well, what you would like to know is how the tunnel for those and ones that succeeded, how that placement correlates with long-term outcome. Well, what you have in long-term outcome are just X-rays, not CT scans. So the idea is from just these uncalibrated X-rays and a statistical model to make our best estimate of the shape and the placement of that tunnel, and then we can begin to do statistical analysis of variability and compare that to long-term outcomes. So this is work in progress that we're quite interested in. Just to finish, in the future, we're talking about medical robots, but the robot in the future isn't going to be what we think of. It's the robot. It's really going to be the operating room. What we're dealing with is an information-rich environment that will have gadgets, imaging systems, video. We can actually watch the surgical team and understand what all they did. And we, in the future, need to integrate all of this information. So this is where we're going. Even for research, this is important. One of the reasons we've been able to make significant progress is we've put a lot of effort into software interfaces that let us reuse the results of our research. And one major thing is something we call the surgical assistant workstation environment that we actually developed jointly with Intuitive Surgical, and it works by curious coincidence really well with their API, but it also works with other surgical robots, including all of our own. And most of the examples I showed you here, in one way or another, we've been using this software environment, it's open source, and we're actually very anxious to develop a larger community of groups to work with. And if you're interested, send me email. Just to wrap up, and I'm going to finish in exactly the time I advertised for once. I've tried really to say what, in my view, medical robotics, or maybe all of robotics, is really a systems discipline, in which the unifying theme is coupling information to action. And in medical robots, there are these information loops at many time scales to help us treat each patient better. And I think more and more in the future, those blue loops are going to create information that will let us actually know what makes a difference and change the way we treat patients. And, I've finished just about every talk I've given in the last 10 years with this slide. And it really reminds me what we're about here. We're really not about getting tenure or getting rich or any of those things. Ultimately, we're about helping people. And I think that actually is one of the greatest rewards in working in this field of robotics. The technology and systems, we have the capability to provide new capabilities that can transcend the limits that existing surgeons have in helping to treat patients. You can also increase consistency and quality of treatments. And in the end, that's going to give us better outcomes. Also, if we can treat people more effectively and get them back to being productive members of society more quickly, it can be very cost effective. So I think this is certainly what I've been spending, probably well over 20 years, closer maybe to 23, 24 years of my career doing, and it's been very rewarding, and I commend this field to other people, and I can also talk about that if you want.